Hi, my name is Ariana. This is my video lab report for Physics 2211 with Dr. Paducah, Lab 4, Oscillations. The purpose of this lab was to determine and predict the motion of a spring mass system by comparing the observed motion with a computational model. The results for this lab were that the change in total energy is zero, and the predicted model and observed model are relatively similar, with the y position graph deviating more than the x position graph. Here are some background concepts before we get into the lab. The first important concept is Newton's second law in the form of the momentum principle, which is used to derive the velocity update formula that is used in the computer model and seen below. It relates the net interaction between the system and surroundings to the observed motion of the system. The formulas below were used in the computer models that predicted the motion of the object over time. Another important concept is the energy principle, which states that the change in energy of a system is equal to the work done on the system by the surroundings and the exchange of thermal energy between the system and the surroundings. The main forces involved in this experiment are force of gravity and spring force. Their formulas are shown and used in the computational model. In this experiment, the system was a mass, earth, and spring, and the surroundings were nothing, as I included everything in the system. I chose the tracker model so that the origin was at the fixed point of the spring and the y-axis was collinear with the spring at rest position. I tracked the model beginning from when the mass was released from hand, and in this model I assumed there to be no friction or air resistance. In other words, no work done by the surroundings. I also assumed the calibration length, mass, spring stiffness, and relaxed length from the video lecture. Here are the initial conditions I set in my computer model. I linked the rest of the code in the slide if you want to take a look at it. So the mass to 0.402 kilograms as given in the video, the initial position to negative 0.12 meters in the x direction and negative 0.67 meters in the y direction as obtained from tracker, the initial velocity to 0 meters per second as assumed that the mass starts from rest, and the constants found using the formula shown and also given in the video are below. Finally, I set up some equations that were used in the calculation portion of the code. In this section of the code, I first establish initial energies. Then I calculate F-net, which is then used in the position and velocity update formulas in order to update the mass's velocity and position. The mass's position is then used to update the spring length, and finally the mass's velocity, position, and the spring length is used to calculate the energy changes. Basically, this code predicts the future using the initial conditions I provided and provides the theoretical data later graphed. There are three graphs produced from the GlowScript code. The top two graphs compare the model versus experiment with the x and y positions, and the bottom graph compares the energy changes. Errors causing deviation between the model and the experiment are tracker errors by not consistently marking the center of mass, video perspective differences resulting in incorrect calibration, and outside forces and energies such as drag force and thermal or rotational kinetic energy. Comparing the top two graphs, there are differences in the amplitudes of the y position model versus experiment, which can be attributed to the errors discussed previously, specifically errors such as not consistently marking the center of mass, incorrect calibration, and not considering outside forces such as drag force, as all of those errors affect the y direction. Both graphs have similar oscillation periods and shape when comparing the model and experiments. In the x-position graph, there is a deviation as time increased, which makes sense because the spring constant was calculated with an average of the first three oscillations. Therefore, it becomes less accurate as time increases. So, is the energy principle satisfied? Looking at the change in energy graph, the energy principle is satisfied. The total change in energy, aka the sum of the kinetic, gravitational potential, and spring potential energy is zero, which follows the energy principle as the change in energy of the system should be equal to the work done by the surroundings. And since we have no surroundings in our model, the change of energy should equal zero. Estimating the oscillation periods from the tracker data, we do find that there is a difference in periods between the x position and the y position by about 0.127 seconds. The difference in periods could cause the deviations we saw in the GlowScript predictions, since the spring constant was calculated using t or period. And this difference could be caused by outside forces and inconsistency when plotting points in tracker. Thank you.